Good afternoon, everybody, to the second IQOQI Colloquium. So today it's a pleasure to introduce Professor Jelezko. So Fedor Jelezko studied physics in Belarus State University, and he got his PhD in 1998 in the same university, and I think with joint affiliation with the University of Bordeaux. Then after that, he moved to Germany, first to the University of Chemnitz, where he was there for a year. And then he moved to the University of Stuttgart, where he was for more than 10 years, so actually from 1999 to 2010, sorry, first as a research assistant, and then he got a tenured senior lecturer position, and in 2010 he got the habilitation there, and at the same year he got different offers, chair, to have a chair in German universities, first in Aachen, also at actually the University of Melbourne, and also the University of Ulm, which was the university he finally accepted. So during all these years, he has gotten many research awards, and I would like to highlight three. In 2008, he got the Walter Schottky Prize from the German Physical Society. In 2013, he got the ERC Synergy Grant together with Martin Pelenio and Tanya Weil. And last year, he got the ZEISS Research Awards, the Research Award. And in the last actually 3-4 years, he has been also listed in the as a highly cited researcher by the Thomson Reuters agency. And his research is very well known for his experimental activity in identifying that perhaps quantum computers doesn't need to be cold. They can be implemented at room temperature with diamond, and in particular with the defects you encounter there. So he realized with colleagues that spin qubits in diamond can have extremely long coherences already at room temperature, and then he exploited that to use these defects for doing nanoscale magnetometry, as well as trying to implement quantum gates and so on. So I guess we will hear about that, so it's really a pleasure to have you here, so thank you very much.
Thank you very much, Aurel, for invitation. It's a pleasure to be here and this afternoon, and I would like to introduce in my talk the flavor of diamond qubits and some of their applications. What you see here, the first slide, is one of the rare cases where in our experiments we are using natural diamond, like this one borrowed from a company, one of the biggest diamond producers. So these natural diamonds have some really rare color centers that we are looking now for potential applications in quantum information science. The application of diamond spin qubits are related to the unique property of diamond material, and I'll give you a very short overview what was done so far using spins in diamond. So we had a rising field of application of NV centers and other color centers in metrology and sensing, so making qubits to be very sensitive magnetometers at nanoscale. Individual atoms in diamond can be also used for generating non-classical state of light to be single-photon sources. And a few years ago, Australian company Quantum Communication Victoria commercialized even a true single-photon source based on individual defect in diamond. This is you see on this device. And couplet diamond defects are interesting in sense of the applications in quantum simulation and quantum computing. All these three areas are very rapidly growing and pursued by many groups around the world. Today, I don't have time to cover all these fields, so I'm going to concentrate myself on magnetometry and imaging, how to use diamond defects for advancing sensing at nanoscale or making new imaging, super resolution microscopy, MRI technique to be enhanced by quantum technology. Starting with microscopy and metrology applications, I would like to give you a general overview of challenges in this field. So if you think about life sciences and medicine and ask biological scientists what is a dream for what kind of tool they would like from us physicists. And if you ask them particularly about microscopy technique, imaging technique, they will tell that they would like to have a microscope that can image single atoms with very high spectral resolution, really like to see 3D structure of molecules. But not only structure, actually, what is important in life sciences is also temporal resolution, that this microscope should be able to image motion of complex molecules in a microsecond resolution. And furthermore, it should basically be able to do it in living cells, ambient conditions. And so far, there is no such a device on the market. So there is a lot of challenges in biology and medicine related to our inability to measure structure of dynamics of complex molecules at nanoscale with microsecond temporal resolution. So our understanding of life is closely related to understanding of structure of proteins. So structure defines a function. So understanding dynamics and structure of protein is a key challenge in life sciences. That there are techniques that are getting very close to this dream list of benchmark for this super microscope. I list you two of them. One of them is optical microscopy. Nowadays, optical microscopy technique is reaching the limit of sensitivities. It is able to measure, to detect, and to track single fluorescent molecules in cells. What you see here is a confocal, so it's optical microscopy image of cells labeled with green fluorescent proteins. In the early days, the resolution was limited by diffraction, but nowadays, owing to super resolution imaging technique like STED or PALM, you can routinely reach resolutions of a few tens of nanometers in this picture. So you can track molecules, but you only can see molecule as a whole. You cannot see atoms inside, and you need labels for this technique. Another technique which is very interesting in this respect is very different. It is nuclear magnetic resonance. It is essentially don't try to reach a high spectral resolution, but it uses our understanding of interaction between spins in the complex molecules to reconstruct the structure. So having a very high spectral resolution in NMR related to long coherence and understanding the interaction inside of molecule make it possible from analysis of this very complex spectrum, this is NMR spectrum where you see in this picture, to reconstruct the structure of proteins. And most of proteins so far were reconstructed, unraveled, using nuclear magnetic resonance. But there are some limitations of this technique. It's intrinsically not very sensitive. So it was not possible so far to measure the spectrum of NMR spectrum of a single molecule. You always had to make billions and billions of copies. And this is not very good often, especially for cases where you want to see heterogeneous molecules, where you want to see molecules which occurs only very rarely. So the very big challenge in this technique is to improve the sensitivity. So what is the problem in sensitivity in nuclear magnetic resonance? So this problem is well understood, and it is related to the fact that most of the nuclear spins are unpolarized under ambient conditions. So you have to compare basically the energy difference between spin up and spin down of a typical nuclear spin like hydrogen with a kT at room temperature. This number is very small. So the Zeeman term to kT is typically on the order of 10 to the minus 5. So out of many, many nuclear spin in a sample, there is just a very small overshoot of polarized spins. And that's what a classical NMR technique is detecting. A very small subensemble of nuclear spin. In addition, the detection technique in NMR is coil-based, and it's not very sensitive, it's noisy. And since a few years, there was quite a big effort to address these challenges, to look on alternative detection technique allowing to enhance the resolution of nuclear magnetic resonance to reach a single molecule, single spin sensitivity. So it's a very big gap that was existing between classical technique and a new technique that are aiming basically to detect single molecule. Just to give you a number, so the classical technique can detect 10 to the 12 nuclear spins. So if you want to go to a single molecule, you have to bridge tens order of magnitude. So it's quite a lot of development that is needed, and it's clear that classical technique, just making coils better, are not really suitable for this task. So new detection technique for nuclear spin is a key point here. Now, the difficulty to detect nuclear spins can be also kind of translated in an energy scale of radio frequency photons. So it's very difficult to detect radio frequency photons, frequency corresponding to nuclear magnetic resonance conditions. The energy of these photons is on the order of 10 to the minus 24 joule, and we don't have very good detectors for this. That's another word of explaining low sensitivity of nuclear magnetic resonance. On the other hand, we have very good detectors for optical photons. So for optical photons, many of you have in the lab, we have detectors that can detect single photons. So in optical domain, our detectors are much better. So the idea about improving detection efficiency in nuclear magnetic resonance is basically combining an spectral information which is encoded in the radio frequency regime and somehow swapping it into a regime where optical photons are. And that can happen if you do have a system, an atom, which do have a long-living spin state associated with this radio frequency region in a ground state coupled to an optical transition. So ability to swap the information from a spin state to an optical regime boosts the sensitivity of nuclear and electron paramagnetic resonance by orders of magnitude. And it was recognized by Castell-Braussel already in 50s and 60s that this double electron radio frequency resonance can significantly enhance the sensitivity of NMR and EPR. Now, the particular system I'm going to talk today about, which combine these properties of being active in a spin world, in a radio frequency domain, and be coupled basically to the optical spectrum, is a color center in diamond. The color center I'm going to talk about is a nitrogen vacancy center, one of many color centers, and I'm going to introduce you how to use this color center in order to make a very small magnetic field sensors enabling NMR and EPR at nanoscale. And essentially, this development are based on three different fields. On one hand is an optical technique to detect these color centers, even in a single site level, single atom level. Another is ability to place this defect in a diamond lattice in a well-defined location. And here material science is very important. I will also give you a flavor of this, how to control the diamond material, and the quantum control techniques enabling preserving coherence of a single spin in diamond for a long time are important. And those techniques are coming often from classical nuclear magnetic resonance, or I will give you a short example in the end of the talk, can be also related to quantum information science. But to start with, I would like to give you a few introductory slides about diamond itself and why diamond is particular material for all these applications. So diamond can be not only created by nature, but also, as we know, since about 60 years, can be realized artificially using two different techniques. One is so-called high pressure, high temperature synthesis. It's It's a way to produce synthetic diamond by mimicking conditions at which they are created in nature. It's a high pressure, high temperature, so conditions where diamond is a stable form of carbon. So this is a press where these diamonds are created, located in Ascot in location of Element 6, the biggest diamond producer company. The other technique is using a plasma assisted growth, where you take a small seed crystal and you put it in a plasma containing hydrogen and methane, and if you choose your plasma condition right, you will get growth of a diamond on top of your seed crystal, atomic layer by atomic layer. And here on the right side you see a picture of synthetic diamond growing by this technique. Those diamonds are the most advanced in sense of the purity. Isotopic purity, they can be created out of only carbon-12 material, but also purity in sense of any impurities created in diamond lattice. I also show you a short movie borrowed by my colleague from Element 6, Daniel Twitch, and will show you how synthetic diamond is grown. What you see here is a seed crystal, and at some point the plasma will be switched on, and you will see how the growth starts and how synthetic diamond now is grown on the top of the seed crystal. So the dimensions here is about 1 millimeter thickness, and you can grow diamond as big as your seed crystal is. After some time you see that you get about 1 millimeter thick layer on the top of the seed. All right, so this is not a video rate, so that can take some time. And I myself also do not know precisely how much this takes in the lab of Element 6. This is a commercial secret. In our lab in Ulm, this would take about a month of growth, so very, very slow. Right, so a diamond is only a host for qubits we are looking for. It's a material which protects electronic and spin structure of artificial atoms that we put one by one inside of diamond lattice. If you want, diamond is a kind of magnetic vacuum for us. So we don't use vacuum chambers, but this diamond is a host that hosts artificial atoms we put in on demand. And the atom I'm going to talk today about is so-called nitrogen vacancy color center. It's actually one of out 500 color centers known in diamond. In structure consists of a nitrogen sitting at the position of a carbon, so substitution of nitrogen atom plus a vacancy nearby. This nitrogen and vacancy form an artificial molecule inside of diamond consisting of 6 electrons. And 2 of these electrons are unpaired, they are optically active as well, and the center possesses spin state which is not zero in a ground state, and also absorb the light and quite efficiently. So the dipole moment of every atom is about 1 dBi, and when present in ppm concentration, part per million, diamond get colored by this pink color, by NV centers. The centers basically have this unique property to have a couplet spin transition and an optical transition. Here is a sketch of the energy levels where you have a ground state electron spins which are connected, both states basically, this is different subspaces of electron spins, so according to magnetic quantum number. So the spin triplet, there's 3 eigenstates with magnetic quantum number 0, plus and minus 1, and these states are connected to excited state triplet by optical transitions. Transitions are very strong, but importantly, one of the spin states have a longer cycling transition than others. 2 of the spin states do have a strong shelving towards the metastable singlets, and this given access basically to readout of spin state and its polarization. By shining a light on a color center, you essentially will be cycling your atom if you are in so-called ms=0 state in one of the spin state, and two other states will not survive for long because they will go to a dark state, which is a Kelvin state, and then will decay into this bright state, which is ms=0 state. So this coupling between spin and optical transition give you access to read out and polarize the spin state of individual atoms. And that is very efficient. It does not require low temperatures or high magnetic field, but just require right illumination of the color center. So the experiment we are going to look for in details is a combination of magnetic resonance and optical microscopy setups. We excite individual atoms with high efficiency lenses. So laser excitation is used to focus the light to diffraction limited spot. We collect the scattered light from atom and detect it using efficient photodetectors like avalanche photodiodes. So in addition to this, so we put a microwave line on top of our diamond, and essentially by sweeping the microwave we can now read the spin state of individual color centers. This is a typical experiment we done maybe 10 years ago where we basically measure fluorescence versus frequency of microwave we shine on a sample, and that's recorded on a single atom. And you see that when you hit a resonance at 2.87 gigahertz here, your fluorescence drops by about 30%. That's because these other states are not a bright state, but the states which go to a Kelvin state are efficiently darker because of the Kelvin, and by measuring the fluorescence, you can say in which state your NV center is. So that's essentially all what you need to know about color centers to understand many of the experiments I'm going to talk about today. But one of the states is brighter than the other, and by measuring fluorescence of single atoms, you can essentially extract the information about its spin state. Now, you can also, of course, look for coherence times of color centers and ability of coherent control of spin state. One important ingredient for spin qubit is ability to polarize it. So we know that we can do it with optical fields. You can also apply microwave pulses, and you can do it also quite efficiently by making very small strip line microwave structure on top of diamond that you see on the left. It's a piece of diamond again with very small wires basically placed somewhere here in the center and implanted in V-center located just between the wire. Can be now controlled by microwaves. When we switch on the microwave and change the duration, you will see Rabi oscillation of individual atoms. So I plot here the population of spin state, which is encoded into fluorescence intensity as a function of duration of microwave pulse, and you can see that Rabi oscillation allow you control your spin state, create a superposition of state by applying a relatively short microwave pulse. It's called pi-half pulse, or applying a pi pulse and inversing the population. The time scale here is about, so for pi pulse about 30 nanosecond, but put in more microwave power, allow you to reach the flip times on the order of a few nanoseconds, 2-3 nanoseconds. So this is a time you need to gate a single color center. So single qubit gate can be pretty fast, but it's a question how it's related to coherence time. For any solid state system, especially for room temperature systems, usually you do have environmental effects that create fast decoherence. Not the case for diamond, at least for very, very clean diamond, where these effects are not very strong. Here I show you the Ramsey fringes experiment, where you excite a coherent superposition of two spin states and wait for some time and then record the phase that is left after, say, precession time. So these precessions are depicted here on the picture. So many oscillations, but those are Ramsey fringes now. And decay of Ramsey fringes happens here on a time scale of a few hundreds of microseconds at room temperature. So it's a pretty good ratio between single qubit gates and coherence time, and that's also recorded without applying any ACOS technique. The immediate application for having the system at hand, what we started to work on, was to realize a quantum register, a small quantum computer, having a few electron spins associated with NV centers, now coupled by magnetic dipole-dipole interaction. And it could be also interesting to have a few nuclear spins around electron spin for storing quantum information for a long time. So the distance between these atoms need to be short enough to allow entangling gate, 2-qubit gate between color centers, to be faster than decoherence. Remember that decoherence is on a millisecond time scale, and interaction that is responsible for any entangling operation in the system is a magnetic dipole-dipole interaction. So it scales as a 1-hour distance cube. It's a relatively long-range interaction, but the prefactor, the magnetic moment of a single electron spin, is not very large. So I plot this interaction and give you a feeling at which distance you need to put color centers. So this is the strength of the coupling between two single electron spins in hertz, and it's a logarithmic scale. It starts here with a kilohertz and ends here somewhere with 100 megahertz as a function of the distance. And this 1 power r power 3, so distance power 3 behavior, give you basically a bound if you have limited coherence time. So if coherence time is on the order of kilohertz, you will see at which distance you can place your color centers to be basically able to entangle them, to be able to perform a 2-qubit gate with thin coherence time. And this distance is on the order of 20 to 30 nanometers. So having a coherence time of a millisecond means that you have to be able to engineer NV centers, engineer the centers in diamond to be basically better than 30 nanometers. And that's not a very easy task. Engineer a solid-state material with high precision of implantation of color centers is very rapidly growing field where a lot of groups in material science are working. There are several techniques to do it. Take focused ion beams. That's usually not very precise. That give you precision of 100 nanometers, but the idea how to improve it. Or take some nano apertures, like a layer of PMMA, or even more kind of advanced approach, a hole in the atomic force microscope cantilever, allowing you to generate this ordered structure. Or what recently we are trying to perform, implanting a molecule. When molecule go into diamond, it creates a few color centers very close by. So this is all avenues of scaling up NV center simulator or quantum simulator or NV center quantum computer, and you need to go beyond 10, 15 qubits to make these devices reasonably well performing. And so this is a kind of a big effort which still need to be done actually to go beyond 3 qubits, 4 qubits for NV center. So fabrication accuracy need to be improved and a few other material science issues. However, there is also an application where you don't need so many qubits to make your quantum register already very reasonable and outperforming any other classical devices. And this application is related to sensing. So even single qubit can be a very interesting sensor, especially if your qubit is small, like a single atom. It can allow you to to gain access to magnetic fields, but now with nanoscale resolution. So measuring magnetic fields with nanoscale resolution have quite a number of applications, like, for example, nanoscale NMR that we have discussed before. So detection of single nuclear spin as other qubits, so read out of other qubits, material science, detecting magnetism at nanoscale, detecting magnetism related to biomolecules. These all are the applications rising from the fact that you now have a qubit at hand, which can be used as a nanoscale magnetic field sensor. So how this magnetic field sensing works? So essentially it's taking a single color center and use it as a small, like a needle of the compass, approaching it very close, allow you to get information about other spins in your molecule. Well, this comparison with compass is maybe too simple. Actually, what we try to do is to make a very small spectrum analyzer. So to not only gain information about the strength of the field, but also about the frequency of the field. And so technique allowing to coherent control of these color centers are crucial to make a highly sensitive spectrum analyzer. So one of the coherent control techniques that is known for about 60 years now is the Han echo. Echo acting on a spin, refocusing unwanted perturbation coming from external environmental noise. So Han echo essentially refocuses coherence of a single qubit having this input state, so propagating in time. So unwanted phase will be refocused by flipping a spin with a pi pulse. So refocusing initial state here. So recover initial state, so it's canceling the local phase, leaving it only in form of a global phase. So this single pi pulse in the middle of the evolution allow you to cancel any DC field acting on a system, and therefore allow you to measure AC fields with high sensitivity, canceling a DC field, right? So this is a kind of a small, not very good spectrum analyzer, allowing you to measure AC fields and canceling DC fields. Now, there are also other variations of these echoes, making it a bit better spectrum analyzer. Essentially, you can place a lot of pi pulses. This is now a train of your microwave control acting on your qubit. And if you place many of those pi pulses in a train, separated by well-defined interval, time interval tau, you will get a so-called filter function of your qubit, meaning a filter function, a window of sensitivity of the qubit to be defined by 1 hour tau, distance between pulses. And so this is a typical filter function for a CPMG pulse sequence having 8 of these pi pulses. So it's a sensitivity function. Sensitivity is y-axis and the frequency is x-axis of the qubit. And you see it have well-defined peaks, now very sharp peaks. And the qubit will be only affected by frequency region of external field acting within this sensitivity function peak. So in other words, it's similar to optical spectrometer also, which do have a sensitivity function. So it's this action of pi pulses is kind of a grating for light going to a spectrometer which select in a photodetector window only a particular frequency of light. This NV center or other spin qubit under action of this train of pi pulses essentially allow you to make the same frequency selection in a microwave domain. And now a single NV center placed close to a molecule can be essentially tuned to be in a very sensitive spectrum analyzer able to detect signal of molecular nuclear spin. So this is a work I'm going to show you very quickly. It's a collaboration with groups of Lukin, Park, and Wordsworth in Ulm that is and aiming essentially to detect individual proteins, individual biomolecule, by placing them onto the surface of diamond, having an V center located just a few nanometers below the surface of diamond. And this NV center will be used now as a small spectrum analyzer. So it gets very, very close to a molecule. And if distance comes to a nanoscale, to about 2 nanometers, the signal from nuclear spin processing in the molecule at Larmor frequency will be detectable by individual color centers. Maybe just to give you a feeling how it looks like, it's all room temperature, and diamond is first functionalized having a carboxyl group. It's a typical chemistry chemists are using. So once you have a carboxyl group, you can attach a protein to it chemically, now bound very firmly to the surface of diamond. This is how atomic force microscope picture looks like. It's topography pictures. And you see that the diamond without molecules, before basically putting molecule on it, is very, very flat. So this is a kind of a scale here, just a nanometer. And if you put the molecule on it, they're very, very dense, like a monolayer of individual proteins. So every of these blobs here is individual protein molecules. In V centers, we don't see here. They, of course, are under the surface of diamond, but in this region, there will be one NV center somewhere sitting just underneath of diamond and see just a single molecule, because it gets so close that it don't see other molecule, because the interaction we are looking for, we are using a dipole-dipole interaction. So it's NV center will always see only the closest part, the closest sample part, which is now individual molecule. And now this is a spectrogram, so recorded with our nanoscale spectrum analyzer. So it's a magnetic noise frequency seen by a single NV center. We are using these XY8 sequences, allowing relatively high spectral resolution. There are 2 spectral regions shown here, and they are essentially 2 peaks which we see in the noise spectrum. And these 2 peaks are related to nuclear spins that are present in the protein. In order to make our experiments more clear, so the protein itself was a very special protein. It was modified to have deuterium and carbon-13 inside. Usually those are pretty low abundance isotopes, but just to make sure that we are looking to the right signals, so we modified proteins with substituting natural hydrogen and carbon with this nuclear spin carrying isotopes, and both spectral lines correspond to noise of molecule induced by molecule at the frequency of Larmor precession of the nuclear spins. So it's a single molecule NMR signals. Now watching of about 1,000 nuclear spin. Remember that classical nuclear magnetic resonance usually require 10 to the 12 nuclear spins. So there is quite a boost of sensitivity. You also can check whether your signals are really NMR signal by measuring the spectral lines frequency, it's Yx, as a function of the external magnetic field. And you can see that they scale as they should scale for given here a magnetic ratio of nuclear spin. You can also use the strength of the signal to localize position over single molecules. So it's a reconstruction, it's a sort of MRI picture of the molecule on top of diamond with respect to NV centers. It's how NV centers see it on the top, and you see that this probability distribution of where a molecule is, and the resolution here is about a nanometer. So NV center, the sensor can point out where your molecule is with nanometer precision. Right. So in the second part, so I have kind of 3 chapters here to discuss. So in the second part, I will quickly give you a feeling how entanglement can enhance the sensitivity and resolution of this diamond magnetometer. So far, we were using just the single spins, and the single spins were essentially used basically as a magnetometer, but without to be entangled with anything. So there was no really, quantum gates beyond 1 qubit gates applied to a system. And the only quantum control we were using was related to application of single qubit gate, these pi pulses, to make a sharp spectral filter function. So here I would like to discuss a little bit how entanglement can be used to further enhance protocols. And especially, I would like to discuss with you the point related to sensitivity of qubit magnetometers. So it's a very general point, and it was discussed a lot in context of different systems, atomic magnetometers, QUID, and so on. And if you want to see what is the smallest magnetic field you can distinguish with your magnetometer, so not the spectral resolution now, but the amplitude of the field, you have to ask yourself what are the parameters of the system. In general, for sensing sequence based on coherent superposition of spin state, then one of the spin state acquire phase, and you measure this phase. Essentially, it's a Ramsey fringes sequence. The smallest sensitivity, or the smallest field, let's put it this way, how sensitivity is defined, is related to parameters of your system. It's a magnetic moment, and then coherence time and total measurement time. So big T is coherence time, tau is the total measurement time, and n is the number of atoms. So in our case, it's just 1. So that's mean that if you want to be more sensitive, so be able to measure smaller deviation of magnetic field, you need to improve your coherence time, be able to measure for longer time, right? So coherence time is fundamentally limiting or defining the sensitivity of any magnetometer, any quantum magnetometer. So if you want to measure, in other words, the energy splitting between spin state, so you want to have very sharp defined energy levels, so long coherence time. So coherence time is crucial parameters, and it's actually the only parameters that define the sensitivity of atomic magnetometer. So coherence time is crucial. So how to improve a coherence time in a system and still be using it for sensing? So coherence is usually in any practical application of metrology is defined or limited by environmental fluctuation. Your spin is not really is isolated from environment, so it sees the environment and it has a limited coherence time. Your environment limited, and that's why you cannot distinguish now anymore your signal, because you have such a strong noise. So the noise is preventing you to measure the signals. What you can do to improve it, as we discussed, you can employ dynamical decoupling technique. Echo, spin echo is an example of it. Echo allow you, for example, to cancel a DC noise and still being able to see AC signals. So echoes have different forms, but usually it's trains of these pi pulses. Yeah, so that's the best that you could do so far, but it reaches its limits. It reaches its limits when the distance between pulses need to get very, very short. If the distance between pulses get comparable to pulse length, then your echo don't work anymore. And it say that, in other words, any dynamical decoupling technique essentially reaches the limit of decoupling for noise becoming Markovian. So the noise is having a frequency component higher than your driving frequency within a pulse. This is the limit of the echo performance. So classical dynamical decoupling techniques are failing against high frequency noise. Now, there is another way to protect your qubit which was developed not in context of classical NMR, but in context of quantum information. And it's a quantum error correction. In quantum error correction, you encode your qubit in a logical qubit, so entangled state of 3, 5, 7 spins, depending on what you want to do, and you detect your ear's decoherence as a kind of a global measurement detecting a symmetry of the system after error happens. And if you can distinguish that the error basically is happening without destroying your qubit, so you can essentially bring your qubit back to the code space. So the quantum error correction essentially is immune against different frequencies of the noise. You just have to make sure that your error does not happen too often, that you can measure and bring your qubit back to the code space within the time interval where probability of having two errors is negligible. So the quantum error correction is very different from dynamical decoupling technique, because its limitations are not in the frequency of the noise, but it's in the amplitude of the noise. Error correction works well for the noise of any frequency, but of the low amplitude. So it's very complementary. So experiment exploring this property of error correction will be not devoted to detect molecules, but just to detect the strengths of the field. So we took NV center, having its electron spin we can manipulate, but also having a carbon, a nuclear spin located about 1 nanometer apart. So I have to say a few words about the small quantum registers. Now, not only electron spin, there is also nuclear spin. It's not a nuclear spin we are going to sense. This nuclear spin is inside of diamond, and it's our auxiliary qubit. This nuclear spin can be read out and polarized from the electron spin of NV center, but it has much longer coherence time. It has a low magnetic moment, but also very weak interaction with environment. It's also not very good sensor, because it has very low magnetic moment. But we try to explore a combined system, entangled system of the electron spin, which is a good sensor, but have a short coherence time, and auxiliary qubit, which is a bad sensor, but having a long coherence time. And now by entangling these two, we would like to have a sensor with a sensitivity of the sensing qubit, NV center, electron spin, and coherence time of a nuclear spin. That's a very special protocol of error correction developed in a special context of the sensing. And the theory work was done by Alex Retzker and Mikhail Lukin. So this protocol is not full-scale error correction, but essentially a protocol allowing you to reach better sensitivity of metrology using quantum error correction tools. So now how it works? So very quick explanation. So we have an electron spin and nuclear spin. Electron spin have states 0 and -1. This is two magnetic states, very sensitive to external field. Nuclear spin have spin down and spin up. And we first prepare this entangled state of two systems. Then we leave them to evolve and acquire the phase. This phase is actually the phase we are going to look for. It's our metrology measurement, so sensing of external fields. Now, if error happens, so a flip on the electron spin, so you get -1 to 0 and vice versa, and this state now acquire wrong phase, certainly, but you can correct it. So from this moment, your metrology protocol will be perturbed. But what you can do, you can essentially disentangle both spin, reset the electron spin and entangle them back. So this is this operation. And what you end up is a state which was happening before the error happens. So by reset of the electron spin, you actively remove the error. This is your measurement and correction step. And you get back your initial state. You can continue to measure. You can continue to sense external field. So your coherence time is longer, your sensitivity is better. Now, this is the result of measurements. So it's a rotation of the qubit by the field we are trying to measure, and we are correcting here the flip error and measuring the phase. And what you see is basically it's a result of measurements where the strength of external field is given by this oscillation. If you don't do any error correction, it's a blue curve, so you lose all the signal. You are behind the coherence time of your qubit. If you apply one round of error correction, you now recover your signal, and the sensitivity of your measurements is given by the slope of this oscillation. So the sensitivity is given here, so how far the system reacts to external perturbations, the slope. If you run 2 error correction steps, you get much faster oscillation. Now your measurement time is longer, and your slope is now higher, so you get higher sensitivity. So far it's possible to run it up to 4 times. So the error correction fidelity itself was not high enough to run it for infinitely long, but improving on this is very crucial, because potentially this technique can allow you to go beyond limits imposed by any material limitations, imposed by redirection even with phonons, which are usually difficult to refocus, and improve the sensitivity of this NV sensors, but I also think that it can be applied for other systems as well. So how quantum error correction, actually protocol designed for protecting the state of the quantum register in quantum algorithm. This is example how it can be used for sensing applications. I also have to maybe make yeah?
So I have a question, Olla. How much do you have to know about your error?
Mm-hmm.
So it's a known error.
The question is, can we protect against any error, right? So the error can be of type of flip or phase. So Sx or sigma x or sigma y or sigma z. So the quantum error correction can protect against any error, but unfortunately, so I think it's a kind of interesting point. So in this case, will enable you to sense anything, because signal you want to sense somehow will also not affect your fully protected qubit. So having a 7 qubit in this register will allow you to get against any error, but unfortunately will not allow you to sense anything. So for metrology, you have to distinguish your error from the signal. And this is done by basically making a signal, for example, to be resonant, and so resonant in frequency, that will be then sigma x on your qubit, and protect against anything which is off resonant. So this is exactly what you need to know here. In this particular case, the error was applied artificially, and it was clear which error it is. But in the same experiments, we also even be able to protect a metrology protocol against natural errors. So, but we kind of were in a situation where one type of error was dominating. So you have to identify which errors it is dominating, and then basically protect against it and shift your signal to the other window. So this is basically how it works. Yeah.
And you can do, you can do 4 times, because each time you apply this protocol, the signal becomes more.
Yeah, that's right. So you see that the contrast get dropped from 1 to 2 error corrections, and dropping of the contrast means that you also lose a slope. And so at some point you bring more errors, that the slope actually get down, so up to 3 you win, 4 sometimes, but it's solely related to fidelity of 2 qubit gates. So every run here is 3 2 qubit gates in a row. So you imagine that 3 runs is 9 2 qubit gates. So if you are not in a kind of not very good regime where you correct yourself, then so this is essential limitation, like in a quantum computer. There is no. Okay, and maybe in a very last minute, so I think I will make it short. I would like to give you a fill-in where you can improve MRI, not necessarily in nanoscale using qubits, but more in a micro scale, and where it can be applied in maybe even a hospital that operates a very big MRI machine. So MRI is a conventional MRI, not single molecule we discussed before, is a very widely spread technique. Every hospital has it. It provides you very sharp pictures of a human body based on basically gradients of magnetic fields and knowing the Larmor frequency of nuclear spins. So it has nothing to do with wavelengths of light, you know, like wavelengths of radio frequencies is an order of meter here. But the resolution can be much better than this. It's again because it uses spectroscopic information. So the resolution, however, is limited essentially by sensitivity. How many nuclear spin I can detect in MRI machines. So the voxel size has nothing to do with wavelengths of radio frequency, but the sensitivity of the machine. So the pictures get unsharp just because they get too noisy if you try to get better and better resolution. So this is how it works. So you get a sample, you apply a gradient of the magnetic field, the frequency, the splitting of nuclear spin up and down depend on the position now in a gradient, and you decode the spectral, so you decode the spatial information by measuring spectral information. So now the sensitivity itself is again very limited because of the very low polarization. We have discussed this in the context of single molecule experiments. Same true for conventional MRI. Even at 1 Kelvin, the nuclear spins, our separation is much less than kT. So you can think about taking electron spins and transferring polarization from electron spin, which is at 1 Kelvin, can be polarized to nuclear spin, and that's a very active field nowadays. Actually, there is a very, very large number of labs working on samples or procedures where you essentially freeze some liquids to 1 Kelvin, put electron spin in it, transfer polarization from electron spin to nuclear spins, and then inject this into a body and measure MRI with higher resolution. That's very, very actively pursued approach. Now, require very low temperature, very high fields, and pretty complicated. So this is a limitation. So idea behind the optical control of spin was to use optical electron spin polarization in V centers that can work even at 300 Kelvin, as you have seen before, of controlling our qubits, and transfer polarization from photons to electron spin of NV center, then to nuclear spin. So that's to make an access to polarize all the nuclear spin inside of a diamond, ideally nanodiamonds, and use this as an agent for MRI. Now, this is a very quick overview of experiments. We took a piece of diamond with some ppb, very low concentration of NV centers, was having here C13 nuclear spins, and first polarizing electron spins of these centers. So this is the PR signal under elimination, and then transferring it to nuclear spins. So I don't go into details of the protocol, how we transfer nuclear spin, and just show you the result. So this is an experiment now performed in a conventional machines. Now not MRI, but NMR, but the same signals. We polarize electron spins with in APR spectrometer, and then essentially transfer this diamond about 100 meters away and measure it in NMR spectrometer how much we won on a nuclear spin site. So the signals are here. So the blue curve, very, very weak signal, is a natural NMR signal. So very, very weak. So if you transfer polarization from optically active NV centers to nuclear spins, you get enhancement of the signal of about factor of 50, and it's on the lower side. So we expect in principle theoretical limits on the order of 1,000 to 10,000. So how this technique can help you essentially to make a larger, much stronger NMR signal and potentially MRI signals. And that can be done, actually, or need to be done in the end in nanodiamonds, small diamond nanoparticles, where you hyperpolarize nuclear spin, you inject them into the body, and you measure them as a signal source for magnetic resonance imaging. Okay. So with this, I shortly summarize what we have heard today. I hope I was able to convince you that color centers in diamond are quite interesting qubits, not only in sense of quantum information applications, but also in sense of application in metrology, like single molecule MRI, or in classical MRI even signals, enhancement of signals by hyperpolarization. So we have also discussed shortly the application of quantum error correction, quantum protocols for improving the sensitivity of these magnetometers in nanoscale. What I was not talking about, but I think it's also interesting kind of a rise in fields for NV centers, is actually use diamond material to build self-assembled quantum simulator based on this special growth of diamond. You can think about growing arrays of nuclear spin inside of NV center and use a dipole-dipole interaction for quantum simulation, reading them by NV center. So this NV center sensing technique can be also used to control and measure very, very large self-assembled array of nuclear spin. It can be actually done for electron spin and nuclear spin both. This is some work we are doing right now. Another interesting avenue of basically future use of NV center, maybe other color centers, is related to ability to map the state of the photons into the spin state and recover it back, like element of quantum memories, element of quantum repeaters, and this is another rising field I was not able to talk today about, or we know time limitation, but just to give you an overview where a lot of development is going on nowadays. So with this, I would like to thank my collaborators, many people from theory to material science, and my colleagues from Institute of Quantum Optics at Ulm University. And thank you for your attention.
So thank you very much for this beautiful talk. So we have time for questions. Are there any? Yeah, maybe then let me, yeah, okay. Oh, Francesca. Yeah, please, let's wait.
Sorry, in the first part of the talk you told us that the diamond is a host, that we have to kind of consider simply an host. Then the question is, how do you choose your host? Can you have a graphene as a host?
Mm-hmm. Yeah, so it's an interesting question. Actually, diamond is a host, and there are many other semiconductors or insulators with color centers. So I personally think that the diamond is very particular host because it do have ability to be constructed from nuclear spin-free elements, carbon. So, but there are many, of course, others, like silicon oxide and other materials, silicon carbide. So I think hosts that fulfill following property being wide band gap to carry color centers, having isotope not carrying nuclear spin, do not have intrinsic magnetic noise, and be constructed from light elements, so related to spin-orbit interaction, so affecting coherence time could be very interesting. And there are other materials like silicon carbide which fall into this area. However, diamond is maybe one of the most studied materials in sense of optical properties and spin properties of defects. That's why NV color center was known for a while, and it was basically not so much spectroscopic investigation was needed to kind of transfer some of its properties to technologies. But I don't think the diamond is the only material.
I actually have a question. So for the sensing applications, in particular with the protocol where you send these pi pulses to adjust the frequency of the magnetic signal you want to measure, I have two questions here. So how, I guess these are microwave pulses, and how important is that these pulses do not affect the source, or does it affect it? Mm-hmm. And second, how do you decide which frequency you are interested in?
Mm-hmm. Yeah, so I think that, let me maybe ask a question whether I well understood it, I'm not sure. You mean the pulses affect the source itself, the source that sent the pulses, or?
No, I mean, you want to detect a magnetic source,
yeah,
and you have the spin qubits there, mm-hmm. and then to make the spin qubit more sensitive, you apply this protocol where you send pulses to the spin qubit.
I see.
Do these pulses also modify the source of magnetic field?
So those, there are special conditions chosen that they don't basically do it so much, because the frequency of your sensing qubits is usually to be chosen to be different from the frequency of the nuclear spin you want to sense. Okay. So the signal you want to sense is tuned from the frequency of the carrier of the pulses, but it's tuned to the tau between pulses. And the tau between pulses can be chosen by, basically it's your choice of you program on the arbitrary waveform generator. So it's kind of you program on your device. So this I think can be minimized. What is, however, not is so easy to minimize is the back action of your sensor to the spins themselves you measure. So this is essentially there is kind of a limitation of spectral resolution. So every time you measure your NV center, you do have some back action on a nuclear spin.
So for this error correction scheme, what you presented, so how reasonable is it that the noise is really orthogonal? Because that's required that this works. And the follow-up on this, so there are sort of new methods around also, which we developed, that you can combine this error correction with fast control in order to sort of get rid of this assumption of orthogonality of the noise. Do you also have experiments planned or done along this line?
Yeah, it's a very interesting point. So, of course, for error correction is important. For conventional protocol, this orthogonality is important. Now, it's an interesting question. We didn't look into like new protocol you mentioned that somehow weakened this condition, right? But I think there is very general condition, a limitation that was already discussed by Francesca, that if you want to fully protect your qubit, so if you want to protect against any type of noise, I think you will fail in sensing, except if you sense non-classical signals. If you, for example, sense not just sigma z or sigma x or sigma y, just like a global field, but you are now looking for a single molecule. And a single molecule do have now couplet nuclear spin. And if you now try to kind of sense a signal which now is related to entangled spins, so that can be combined with protecting of your sensing qubit from a global field. Sigma x, sigma y, sigma z. So that can be combined. Otherwise, if you sense more like a field of type of sigma z, for example, then you cannot run the full protection and be able to sense. But I think it's very interesting to look into kind of variation where like sensitivity window can be constructed by applying more developed error correction protocols.
So I'm a very big fan of your work. So that's why I do so many questions. So related to the last part, okay, was maybe a bit faster. I didn't got. So you showed how you could increase exactly this. So it's really amazing how much this peak kind of can increase. But there is a broadening as well. Is this now, I don't know if I understand completely I don't understand at all what is the chemical shift, but somehow is now this broadening something bad, like blurring the signal, or is it, I don't know.
Yeah, so in this case, so I'm actually not sure that, well, I think there are several reasons for this broadening, but I'm not sure actually there is a broadening between blue line and a red line. So the red line seems to be broader here, but if you look in the half width, I think it's very similar. So it's the line width of carbon-13 spins in diamond can be partially related to the dipole-dipole interaction in this particular case, and so it's larger than chemical shift. I think what we see here is a residual interaction between nuclear spin, which also can be actually compensated by decoupling. But I think that the effect here, like it seems to be that it's broader, but I think that it's actually effective that it's kind of scaling here. So from what I kind of know, that the line width on both lines is essentially the same. So the electron spins present in to cool the nuclear spin potentially can broaden the nuclear spin, but it's for this concentration it was actually, if you see here, it's okay. So it's, if you see here in this picture, so sorry. So the concentration of this electron spins in this diamond it was very, very small, 0.02 part per million. So the nuclear spins present in the sample don't see so much perturbation from the electron spins.
Yeah. So regarding the application of using the spin qubits for quantum computation and so on, you commented that there is the problem or the challenge of how to couple long-distance spin qubits, because magnetically we have the limitation of these 30 nanometers. Could you comment a bit about the state of the art of other possibilities or ideas?
Yeah, so there is, of course, several ways to couple spins. So one of them is couple them via photons. So they have this intrinsic channel. And there was a very spectacular demonstration of entanglement over long distance by Roland Hansen group in Delft. In a way that basically entanglement is probabilistic. And we need to work hard to make the rate of entanglement higher, to go beyond 2. And so this is essentially related to collection of photons, given the rate of interference of the photons to be large enough to get high rates of entanglement. So this is one of the applications. So the other is to make entanglement even deterministic, still based on optical dipole-dipole coupling, by placing 2 qubits, but now about a wavelength apart. So where optical photon wavelength is comparable to distance, then essentially there are schemes where you can entangle two qubits based on the optical dipole-dipole interaction, requiring now fidelities of about a micron, which is already much better. And last but not least, there is quite an effort now to explore new interconnects, like mechanical one, where you place diamond qubits inside of a cantilever, and now a common vibrational mode that bends the cantilever will affect spin qubits and can allow entanglement. So there are several ways which are exploring some kind of a different way to couple them. This direct dipole-dipole interaction between electron spin is maybe the simplest way to have it, but also have some interesting properties. For example, in the context of quantum simulation, so you use now simple dipole-dipole interaction to simulate dipole-dipole interaction, because often what you want to simulate is magnetic materials consisting of spins. So having a spin at hand as an element of quantum simulator and use the dipole-dipole coupling can be quite interesting for application of quantum simulation in a solid-state systems.
So, I mean, you've shown that you can sort of detect what goes on in a single molecule. I mean, are you also thinking about sort of applying these techniques to sort of look at interfaces? Because that's sort of a little missing piece in material science, that I could have something which sort of really looks at the stuff close to the surface or interfaces in general. I think a lot of people would love to have that to figure out what goes on there.
Right. Yeah. So I think it's a very interesting point. And actually, we looked actually on interfaces. And in the first experiments, we tried to detect single molecule. We had too strong noise from interface, and we actually measured the noise spectrum interface before even we detected molecules. And there was quite an effort to to do chemistry to reduce the number of parasitic electron spin on the surface to be able even to see the molecule. So indeed, so this can be quite interesting for measuring the interfaces and understanding the spectrum of noise coming from interfaces. And so I'm not sure that it's applicable to superconductors, but it well can be. So I think it's kind of an interesting aspect of it. Yeah.
Okay, any further question? Okay, so if this is not the case, let's thank the speaker again. And you are all kindly invited. There will be some coffee and pastries outside so that you can also talk with the speaker. Thank you very much.